Okay, so in the last lecture, I finished introducing threads. Before I go on, the next thing I want to talk about are mutexes and sharing data between threads and so on. But before I do this, I want to interject a little bit of a discussion about some important concepts that relate to concurrent programming. And I want to introduce them kind of earlier because they're things that I find often trip up students who are relatively newer to concurrent programming. So in particular, what I want to look at is what's referred to as a happens before relationship. So if we have two operations in some concurrent code, for example, these could correspond to operations on different lines in different threads in the program. You have some operation A and an operation B. So they can be in the same thread or they can be in different threads. It doesn't really matter too much. We say that the operation A happens before B if the effects of A become visible to B before B is performed, before performing the operation B. And the key thing in this definition is visible. When we say happens before, it doesn't mean, it's a much stronger condition than happens earlier in time. So happens before does not mean the same thing. Like if you ask your grandmother, what does happens before mean? Assuming she's not on the C++ standards committee or something, she's going to give you the wrong definition of happens before. Just define it as like happening earlier in time. It does not mean it happens earlier in time. That's kind of part of it. It's a necessary but not sufficient condition for happens before to be satisfied. The important thing is the visibility. And in practice, when we're writing code, really what we care about is the visibility of results. So if there's some other thread has computed some result, like maybe 10 minutes ago, but I can't see that result, it doesn't matter to me that it's been computed. I can't see the result. I can't use it. It's useless to me. So in some sense, happening earlier in time is not really that important with respect to concurrent programming. What matters is whether you can see the results that were computed earlier in time. And the reason that you might not be able to see them is this thing called caches and all the other optimizations that are performed both by hardware and also by the optimizing compiler as well. These changes or optimizations that are performed can have the effect of delaying the visibility of results, making it take much longer for you to see results than you would otherwise expect. And I have an example on the next slide to maybe elaborate a little bit more on this. Happens before relationships are not transitive in C++, but only in certain kind of special case, which involves something called a dependency ordered before relationship, which I'm not going to talk about and you're not responsible for. So because I'm going to ignore this particular type of relationship, the so-called dependency ordered before relationship, the happens before relationships become transitive. Transitivity just means that if A happens before B and B happens before C, then A happens before C. This actually is not true in C++, strictly speaking, because of this weird kind of relationship here, but I'm going to ignore it. We're not going to do anything in our code which would use it. So from the point of view of what we're doing, it's safe to think of happens before relationships as being transitive. If they're not transitive, then things just get really complicated and it's really not worth considering. Anyway, any questions so far? Okay. So I have an example here to try to illustrate the difference between earlier in time versus happens before. So what I have on this slide here is a code example where we have a program with two threads, and we have two variables x and y, which are integer variables that are initially 0, and these variables are both visible by both threads or accessible through each thread. And the first thread, what it does is it does a write to the variable x, assigning it the value 1. And thread 2 just consists of a single line. What it's doing is it's reading the value of x and assigning it to y. And I'm going to refer to this operation as operation A and this operation as operation B. Suppose now that the code, and I'm also going to make another assumption, which is that all memory accesses are atomic, so we don't have to worry about data races and so on happening in the example that I'm about to go through. And what I'm going to consider now is suppose that the two threads run with the specific timing that's shown in this diagram below. So this is the time axis going downward on the slide. So what's happening first is thread 1, which is running on core 1, it assigns 1 to the value of x. And I'm going to refer to this as operation A. And then thread 2 at some later point in time, because this is further down on the slide and time is running downward, this is going to read the value of x and assign it to y. And I'm referring to this as operation B. Now, a very fundamental mistake that a lot of people make when they're new to concurrent programming is they say the value that's read by thread 2 here is going to be equal to 1. And the incorrect logic they have is, well, this line of code here, which set x to 1, happened earlier in time than this line here. So of course, because it calculated that value, it wrote that value earlier in time, how could I not see it in thread 2 when I read the value of x? The problem, though, is you are probably not going to read that value. There's no guarantee that the value that you read on this line in thread 2 is going to be the value of 1. It's irrelevant that this operation here happened earlier in time. Because when we're writing code, what we care about is not that something happens earlier in time. That's not good enough. It has to happen earlier in time, and the results that were computed earlier in time are visible at the point where we try to use them. So in this particular case, there is no happens before relationship between A and B. Therefore, we don't know what's going to get read for X here. And again, it's really important to understand visibility. And if it's still kind of perplexing to you, like, why is this the case? I mean, think about caches. So the example I would use is, suppose that each of us is a core. So like I'm a core, and we have like a large multi-core processor with a whole bunch of cores. So each student is a core, I'm a core, and we're all sharing a global variable X. So I'm going to write the value of X. So I write the value of X. I have a write back cache. So my cache, when I write the write operation, I write to my cache only. This is what a write back cache does. And then only later, when that block gets evicted from the cache, do I propagate that value out to memory. So again, like, assume all of us have write back caches, but the most important thing is I have a write back cache. So I write the value of X. I've written it with a value. So this is happening earlier in time. Then I'm now going to ask you, what value did I write? Clearly, I wrote the value earlier in time. I just said I wrote it now. So it's now later in time. I'm asking you, what value did I write? And the correct response is just a blank stare, like what I'm getting. Well, of course, I can't tell you what it is. You didn't tell me what it was. But I did write it earlier in time. The problem is it only got written into my cache. And the cache is private to me. You can't see what's in my cache. So it's kind of irrelevant to you that I've computed this value and written it, because you can't see it. And this is what I'm talking about when I'm talking about visibility of results. This is all what the happens before relationship is all about. It's not good enough something happens earlier in time, because usually you don't just care, did something happen earlier? There's some result that was computed earlier that you want to use. And the question is, can you see that result? And it's because of caches and other optimization that's made by the hardware, and maybe some transformations applied to your code that's done by the compiler, which can effectively delay results from the time that they're generated to the time they can become visible. You know, for example, so an example that I was just describing, until I actually flesh out my cache, if you actually read the value of that variable X, what you'll get is one of two things. Either you have that value already cached, and then you just read a stale value out of your cache, which is not what I wrote. Or maybe you have to go to main memory because it's not in your cache, and you read the value in memory. But that's still not the value that I wrote, because my value has not been fleshed out of my cache into main memory. So this is the kind of thing that can cause problems with respect to visibility of results. Caches effectively can cause memory operations to take very long periods of time to finish. When you do a write, it may take a long time, for example, with a write back cache, for that data value to propagate into memory. And even if it does go into main memory, if you have a stale version in your cache, you'll still read that value out of your cache and get the wrong value anyway. So these are the sorts of issues that can arise in concurrent programming that are not really issues in the single-threaded case. And they cause a lot of complications. In terms of what things happen before relationships to exist, this is kind of a separate issue, which we're going to discuss a little bit more in detail as we proceed through. But the bottom line is, sort of statistically speaking, almost nothing guarantees it happens before relationships. So unless there's something that says that there is one, you're basically best to assume that there isn't. And the common mistake I often see with students when they're first writing concurrent code is they just assume, well, this happens earlier in time. Of course I can see the results that were produced by this earlier computation, when instead you should be thinking, I cannot see it unless I can see some evidence, some documentation in the language standard, or something in the library I'm using that guarantees that there's a happens before relationship. But most things don't make this guarantee, because there's a performance cost. It requires synchronization between the processors to make sure that their cache data and stuff is in agreement with one another. So typically you don't have this unless you kind of go out of your way to make it happen. Any questions? So a few other types of relationships that all kind of relate to this happens before notion. So the next thing I want to talk about is what's called a sequence before relationship. And in terms of the relative difficulty of understanding some of these concepts, this is one of the easier ones to understand, I would say. So if we have two operations, A and B, that are in the same thread, so this is critical. We're talking about stuff that's happening in the same thread. The operation A is sequenced before the operation B if A precedes B in program order. So in other words, in terms of the order in the source code, A comes before B. So to use an example with this code down below here, all of this code is running in the same thread. And we'll call the first line operation A, second line operation B, and third line operation C. In terms of the terminology that was just introduced here, A is sequenced before B because A comes before B in source code order, in program order. And B is sequenced before C because B, this line here, comes before this line here in program order. In other words, the order it appears in the source code. Sequence before relationships are also transitive. So if A is sequenced before B and B is sequenced before C, then A is sequenced before C. It just follows kind of the logic that you would expect. And this is kind of a simpler definition because it's only concerning itself with one thread at a time. Any questions about this? Okay, so this is what we call a sequence before relationship. A little bit more about sequence before relationships. Well, I guess I kind of commented on some of this stuff before, but just to emphasize, like this is a relationship that talks about what's going on within a single thread. So it's sometimes referred to as an intra-thread relationship. Intra means within. It's different from inter. So a sequence before relationship implies a happens before relationship. So if we look at, I think this is the same code we were looking at on the previous slide. We have that A is sequenced before B, B is sequenced before C. Because of this, since A is sequenced before B, A also happens before B. And because B is sequenced before C, B happens before C. So the sequence before relationship implies a happens before relationship, sort of as you would expect. It sort of makes sense. But here we're still dealing with just a single thread. So this is what makes this kind of, relatively speaking, easier to understand, I think. Any questions? So the next type of relationship that I want to talk about is what's called an inter-thread happens before relationship. So if we have two operations, A and B, and they're in different threads, this is the key thing here. It's an inter-thread relationship, inter meaning between different threads, essentially. So we have A and B are two operations in different threads. We say that A inter-thread happens before B. If this is true, then A happens before B. So effectively what this is a way of saying we have operations in two different threads and one is happening before the other. It's like a happens before relationship, but it's between things happening in two different threads. Inter-thread happens before relationships are transitive. So if inter-thread happens before B and B inter-thread happens before C, then A inter-thread happens before C, which is kind of the intuitive sense that you would have of how things would behave. In order to have such a relationship hold, in other words, in order for an inter-thread happens before relationship to be present, there has to be something special happening. There has to be some kind of synchronization. Processors need to talk to each other to make sure that they see a consistent picture of memory and so on. Because with caches being involved and so on, it's very easy for processors to disagree about what's stored at any given memory location. Anyway, so generally you don't tend to have these kinds of relationships on something unless something very special you do forces it to happen. Any questions? So this slide just kind of summarizes things. So essentially what we have in general, we have two operations, A and B. They might be in the same thread or they could be in different threads. If they're in the same thread, then really what we're interested in whether one is sequenced before the other. In other words, the source code order effectively dictates whether there's a happens before relationship between things. But this is kind of the less interesting case. The more interesting case is when A and B are in different threads. In this case, we have a happens before relationship between A and B if A inter-thread happens before B. And I think most of this other stuff I've covered. Having been introduced to inter-thread happens before relationships, I'd like to introduce another type of relationship that can establish an inter-thread happens before relationship. And the particular relationship I'd like to introduce is what's known as a synchronizes-with relationship. So for two operations A and B that are in different threads, if A synchronizes with B, then A inter-thread happens before B. In other words, a synchronizes-with relationship establishes an inter-thread happens before relationship. So in this sense, synchronizes-with relationships are quite important because they can help us to establish happens before relationships. So to further illustrate the notion of a synchronizes-with relationship, I have a code example on this slide. In the code example, we have a two-threaded program where the two threads are sharing a variable x of type int, where x is initially 0. And we also have appearing in this code a call to a function called foo and a call to a function called bar. And for the purposes of this example, we're going to suppose that these functions foo and bar have certain properties. In particular, we're going to assume, first of all, that any calls to the function bar will block until the function foo is called for the first time. And the second assumption that we're going to make is if a call to foo is made prior to a call to bar returning, then the call to foo synchronizes with the return of the call to bar. And you can think of this as if this is part of the documentation for these functions, and these are some functions in a library that we're using. Now, in this particular example, it turns out, due to the way in which the functions foo and bar are defined and the way our code is written, that the call to foo in thread 1 is always going to be made prior to bar returning in thread 2. So because of this, the operation that we have labeled as A here, which is the call to foo, and its relationship to the operation that we've labeled B here, which is the point where we've returned from bar, the relationship between these operations A and B is such that A synchronizes with B. And this in turn implies that A must interthread happen before B. And then this in turn implies that A happens before B. And because of this, the assertion in thread 2 that X must be equal to 1, this assertion can never fail. The reason why is, again, because A happens before B due to the synchronizes with relationship. This means that any state that's modified before this point, A, must be visible to the operation that's being performed at B. So part of the state that's being changed prior to A is setting X equal to 1. Therefore, when we reach this point B, that change must be visible to us. Therefore, we must see a value of X being 1. Therefore, the assertion here must pass. So earlier we were talking about threads, and we looked at two basic operations for threads: creating threads, essentially the constructor for a thread, which creates a thread, and we looked at the join operation for threads. These operations both introduce synchronizes with relationships. And if this wasn't the case, then maybe some of the code that we've been looking at so far might not work correctly. I can't remember, but at least some of the subsequent code we look at definitely wouldn't work correctly if this was not the case. There's also some other things that introduce synchronizes with relationships. We'll talk about mutexes later. Mutex lock and unlock operations introduce synchronizes with relationships. We probably won't talk about atomics in this course because there's just not time. But there's some other, this is not an exhaustive list. There's a number of things that provide synchronizes with relationships. I just tried to highlight the ones that are most relevant to us in this course, which are the first three that are listed on the slide. And to give a more detailed example about what I mean with synchronizes with and in the context of thread creation and thread joining, I have a code example here where I have a function called doWork, which I'm going to start up a thread to execute the body of this function here down in the main function below. And I have a number of assertions in this code, actually two. There's an assertion here, an assertion down in here in main. And the claim that I'm going to make here is neither one of these assertions can ever fail. And the reason why they're guaranteed not to fail is specifically because of the fact that there's some synchronizes with relationships that are guaranteed by thread creation and the joining of threads. So if we look at, and the key thing that we're doing here is we're doing assertions on values of X. So what we're really interested in this example is how X is being changed and when these changes become visible to different threads at different times. So initially X is 0 because it's a static storage and it's initialized to 0. So before the program starts up, it has the value 0. Then inside main, what we're doing is we're assigning 1 to X. Then we create a thread, which is going to be executing the function doWork from up above. Then we join with the thread, and then intermixed with this code, we have a bunch of assertions that we're executing. So what I want to do is I want to look at each one of these assertions and explain why they can't fail. In other words, why the code is guaranteed to have the behavior that neither assertion can fail. So if we look at the first assertion here, when this assertion gets hit, this is when the thread is executing this function doWork. So essentially what we're looking at, I've labeled, just for convenience, I've labeled this assertion here as operation A1. So A1 corresponds to basically when we're just starting the doWork function, we've just started up the thread. It's starting to execute. I've labeled A2 as the end of the thread execution. So it's just when we're falling off the end of this brace bracket here and the thread is finished executing the body of this function. And then I've also labeled this point M1 in the source code. This corresponds to when the constructor returns. So we've just finished constructing this thread. This is the point in time that's sort of labeled as M1. And then M2 is labeling the point where we've just returned from the join function. And if we go back to this assertion here can never fail. And the reason why is that the point in time that I've labeled as M1, it synchronizes with A1. So if we look at M1, this is the completion of the constructor that creates the thread. And then A1 is the start of the execution of the thread. And if you look back to the previous slide, thread creation, what it does is it introduces a synchronizes with relationship between the completion of the constructor that constructs the thread and the start of the execution of the thread. So because M1 synchronizes with A1, this means that M1 happens before A1. So because M1 happens before A1, this means that any state changes that happen before this point, including this assignment to X, must happen before A1 occurs. And since this assignment here must happen before this assertion is checked, this means that when we do the assertion check, X must be equal to 1, because this point in the code happens before the point where we're checking this assertion, like in terms of happens before relationships. So we're guaranteed that this assertion is going to be true because X must be equal to 1. Any questions about that case? Then if we look at the other assertion that we have in the code here, asserting that X is 2, the reason why this assertion can't fail is we have kind of 2 points that are synchronizing with one another in the code. We have a synchronizes with relationship between A2 and M2. So A2 is the end of the execution of the body of this function for the thread, so the end of executing this do work function. And M2 is the point where we're returning from the join. So what we're guaranteed, again, this is guaranteed by the join operation, and the specification of the library, the specification of the thread class, it says that the join function introduces this kind of synchronizes with relationship. So in other words, we know that A2 synchronizes with M2. In other words, the end of the execution of this thread function here happens before we return from the join function, because there's a synchronizes with relationship between them. So because this the end of this function here happens before we return from this join function, it means after we return from this join function, any state was changed anywhere inside the body of this function here must be visible to us, because all of this stuff in this function happened before we've returned from this join function. And because the last thing that was done inside this function here, the thread function, was setting X equal to 2, because of this, when we assert that X is equal to 2, this must be true. If, for example, thread creation and thread joining did not make the promise of introducing, synchronizes with relationships, this code would not work. You could get these assertions failing. So that it's really critical that we have these happens before relationships between different parts of the code. And again, they're coming from these synchronizes with relationships. So in the documentation for whatever library functions you're using, you may encounter stuff where it says as part of the API specification for the code that you're using that certain operations introduce synchronization like this, synchronizes with relationships. And these are very important things to pay attention to, because essentially these are the things that allow us to deduce something happening in one thread happening before something in a different thread. Any questions? So with that said, what I want to do next is just go on and look about sharing data between threads and looking at the various issues that arise when we're doing this. So in multi-threaded programs, we often have resources that are shared between different threads. This is the reason why we would probably put multiple threads in the same process to begin with, because the processes, all the threads within a process share the same address space and also share other resources as well, like open files and open network connections and so on. So probably the reason we've chosen to put them in the same process is so that they can share some of the resources that they're using. But when we start sharing resources between threads, we can run into lots of different problems. What I'm going to focus primarily on is when we're sharing memory. Memory is the most common resource that's shared between threads because you put them in the same address space, so they're all accessing the same in memory. Therefore, we can share variables and so on between them. And when we're sharing variables, then the issue that arises here is we can have things like data races, because as soon as multiple threads can access the same data at the same time, then we have the potential for data races. So then how can we avoid having data races? This is the sort of thing that we want to look at in the subsequent material that we go through. And even if we don't have data races, we can also still run into race conditions, like problems where due to the particular timing in which the code executes, we may get results which are not what we want, like not correct results, due to the fact that they're shared resources. There may not be a data race, but we can also get other inconsistencies arising. And I'll look at this in more detail as well as we go through some of the subsequent slides. So a little bit more terminology. I need to introduce the notion of what's called a race condition. So a race condition is simply a situation where, depending on how the timing of the code proceeds, you can get different sorts of results. Maybe to use an analogy, if you imagine that you're like queuing up, like lining up to purchase some tickets for a concert or something like that, depending on when you arrive at the queue, you could get a different result. One result might be when you finally get to the front counter, there's still tickets left and you're able to successfully purchase a ticket. Other possibilities, maybe by the time you get to the front counter, they've run out of tickets and you can't get a ticket. So depending on the timing of like when you arrive and queue up for the to purchase a ticket, you may have a different kind of outcome. So this is what I mean by race condition. You can have similar things in code where, depending on the timing with which particular parts of the code execute, you can get different kind of results. And sometimes the results may not really be a problem. In other words, the race condition may be benign. It's not really an indication that anything's wrong. You just naturally get something different happening. But usually when we use the term race condition, we tend to use it in a way where it's indicating something's not benign. In other words, it's causing something wrong to happen, some incorrect behavior in the code due to a particular timing with which the code is being executed. One example of a race condition is a data race. This would be a very, very evil kind of race condition. It's very evil because as soon as you have a race condition of this type happening, in other words, as soon as a data race occurs in C++, your program has undefined behavior. So you literally don't know what your program is going to do when you execute it. So this is like a really extreme kind of consequence of a race condition. But there's lots of other types of race conditions. Data races are not the only type. There's a few kind of categories of race conditions or consequences of race conditions, what we call deadlocks and live locks. So a deadlock is a situation where two or more threads are trying to make some progress, achieving some goal, but neither one is able to achieve progress due to both of the threads being blocked. They're basically not doing any useful work, but they're also not making any forward progress with whatever it is that they're trying to do. And the analogy I would use to kind of describe a deadlock is, imagine that two people are approaching a door from opposite sides of the door, and the door is narrow enough that two people can't fit through at the same time. So an analogy that would illustrate the notion of a deadlock is you have two very selfish people approaching the door. So the first person says, "I'm not moving out of your way, get out of my way," and they just stand there and block the door. And the other person says, "I'm not moving either, I'm just standing here and I'm going to block the door." And they both just stand there. They're not doing anything else, they're just standing there, not doing any further processing or anything, no communication, they're just refusing to move. This would be analogous to a deadlock. And then we have what's called a live lock. A live lock still has a situation that two or more threads are trying to do something. They're not making any forward progress to achieve that goal. But the difference in the case of a live lock is they're still doing something. They're actively consuming CPU, achieving no useful purpose. Like, they're not making forward progress. And the analogy that I would use for a live lock is, again, suppose you have two people approaching a door that only one person can fit through at a time. But instead of them being very selfish, they're both very selfless people. So the first person says the second, like, "After you, please." And then the other person says, no, I insist, after you. And then they keep going back and forth forever, just saying, no, I insist, after you. So in this case, they're actually doing active work. They're just saying, no, after you. So they're doing something, but they're not making forward progress of the goal of moving through the door. So this is what we would refer to as a live lock. In the end, both of these are kind of equally bad because they end up with you not being able to achieve any forward progress in your code when they occur. But they're different in the sense one of them is sucking CPU, doing nothing, whereas the other one, basically things are just not doing anything. But both of them typically cause undesirable effects in your code. Things typically will tend to start hanging when that happens. Anyway, so this is race conditions and so on. Any questions about any of those terms?
Next, I need to introduce a few more concepts related to the sharing of resources between threads. Namely, I need to introduce the notions of a critical section and mutual exclusion. So a critical section is simply a piece of code that accesses a shared resource that must not be concurrently accessed by more than one thread. So in order to ensure that more than one thread does not concurrently access the shared resource in question, a critical section must not be executed concurrently by more than one thread. In other words, the execution of critical sections by any two threads must not overlap in time. And the requirement that no two threads be executing code in critical sections at the same time is known as mutual exclusion. In order to achieve mutual exclusion, some form of synchronization mechanism is needed at entry to and exit from critical sections. By using such a mechanism, threads can coordinate with one another to ensure that no two threads execute critical sections concurrently. So to give an example, suppose that we have a FIFO queue, in other words, a first in, first out queue, and it's shared between two threads where one thread is adding elements to the queue while another thread is removing elements from the queue. There's the potential that one thread could be adding an element to the queue at the exact same time that another thread removes an element from the queue. And if this happens, there's the possibility that the queue data structure could get corrupted because there could be race conditions, there could be data races, all kinds of bad things could happen. So in order to ensure that bad things don't happen, some kind of synchronization needs to be employed so that the execution of the parts of the code that add and remove elements are executed in a mutually exclusive manner. In other words, they can't run at the same time, so that the possibility that one thread could be trying to add an element to the queue at exactly the same time another thread is trying to remove elements, this can't happen. They're not actually updating the data structures at the same time so that you can have data races, race conditions, and possible corruption of the queue data structure.
So just to make it a little bit more concrete with a specific example, so suppose that we have some kind of bank application where we're trying to maintain the balance in our bank account, and we have two threads that are managing or basically performing some operations with respect to our bank account. So we have our current balance, which is a global variable, and then some amount we want to credit and debit the account by. So we have the first thread here, which is doing the crediting part. So it's going to read the balance and then increment it by credit and then write the value back. And then we have another thread here, which is going to be performing a debit operation. So it's going to be subtracting some amount. Basically, it reads the balance, subtracts some amount from it, and then writes the value back. This particular code here, at least as it's written, would have a data race, because there's nothing really to make sure that these two pieces of code don't access balance at the same time. And they're basically both doing read and write operations to it. Essentially, this is like a read, modify, write operation. It reads the value of balance, modifies it by adding credit to it, and then writes it back. So both of these operations are performing writes. So this can introduce a data race. And we can end up with all sorts of weird sort of behavior. And by the way, there's no guarantee that this increment operation is atomic. Like, for example, the best way to visualize it is you essentially have a temporary variable. You read the value of balance into this temporary object, then you add the credit value to it, and then you write this temporary value back out to balance. There's not any guarantee that this can sort of be done all at once without any intervening memory operations from other threads. So because of this, we have data race. We could be writing to the value of balance here at the same time we're reading or writing here. So how can we try to prevent this sort of situation from arising? Another example of some code that has some data races would be this example here, where what we have is we're a function which is representing the code that we're going to have a thread execute. So this is a function for a thread to execute, and we're creating two threads, T1 and T2, both of which are going to run this function. And all this function is doing is just basically we have this global counter, and it's just incrementing it, and it's running for a very large number of times. You have 1 million iterations. It's just going to keep incrementing counter until it's done it 1 million times, and then basically finishes. And then, of course, we join with both of these threads. Otherwise, we're going to have some problems if we don't do this. And at the end here, we print out the final counter value. What you might be inclined to expect is when all is said and done, because there's two threads running and each one of them increments the counter 1 million times, you'd probably expect that the value of the counter at the end is 2 million. This is probably what the intention of the programmer is. In this case, though, this is unlikely to be the case in practice. And basically, the behavior of this program is going to be undefined because we have a data race. Can anyone see what the problem is in this particular code? Like, what is it that's going to give us the potential for a data race? Mm-hmm.
Both accessing counter and incrementing it. And so when one reads the value and then increments it, the other one might be writing the value.
Right. But basically, both of them are doing lots of reads and writes. And if both of them are reading, it's okay. But eventually, you're going to hit the case where one's reading, one's writing. It's happening at the same time. And then, like you said, you're going to have a data race in that situation. So as soon as this happens, I mean, because this code has a data race, immediately what we can say about the code is that it has undefined behavior, because this is the way the language is specified. So what this means is we literally don't know what this program will do when we run it. Probably in practice, for like most architectures you would run on, the most likely outcome is probably it won't crash. What will happen is that the counter value is very unlikely to be 2 million at the time the program finishes. What will be more likely to happen is probably the value be something less than 2 million. It could be a lot less than 2 million, or maybe a little bit less, but essentially some counts are probably going to get lost due to the two threads having sort of data races on this counter variable. Another example here. So here what we have is a little bit more complicated example with a integer set, this class called IntSet. So it's a very simple class that implements a set of integers. And it has essentially two interesting functions. It has a function where you can add an integer to the set, and it has a Boolean, like a predicate, that allows you to test to see if a particular integer value happens to be in the set or not, and it just returns true or false. And then this is implemented underneath by using unordered set from the standard library. And then what we have in the main function here, we have this global variable S, which is going to be shared between all the threads that we create. And we're going to create two threads, one that's T1 here and one that's T2. And what T1 is going to do is going to loop, and it's going to insert, I guess, a bunch of even integer values. Basically, it's looping from 0 up to, but not including 10,000, and then it's introducing a value of 2 times I into the set. So it's going to add like 0, 2, 4, 6, 8, something like this. And then we have another thread, which is essentially adding values that are 2I plus 1. So we're going to get kind of odd integer values being added. And then at the end, of course, we join with both of the threads to make sure we don't run into any problems. And at the end, what we're doing is we're just printing out, does this container hold the value of 1,000? And probably what the programmer was intending when they wrote this, I mean, this loop here is going to introduce a value of 1,000 at some point, because it's essentially introducing a whole bunch of even integers into the container. So probably what was hoped for when the person wrote this particular code was probably that eventually it's going to print out true, or basically print out a value that indicates true that this value is contained in the container. But probably what's going to happen in practice is this is just going to crash, probably with a segmentation fault, some kind of very violent failure. Can anyone suggest what might be the problems that are associated with this particular code in terms of some of the things we've been talking about so far in the course? Think in terms of things like data races, race conditions, things of this sort of nature. I'm not trying to introduce any kind of new things that we haven't talked about. It's kind of like more of the same sorts of issues we've been talking about so far.
So what happens if you try to insert two elements at the same time? If it needs to do something like reallocate the buffer, what actually happens?
Right. So for example, there's nothing to prevent, like both of these threads could call the add member function at the same time, for example. And then underneath, when we call add, what's happening is that like the problem won't really be an add per se, like in the actual body of add, but add then calls insert. So we're kind of punting the problem into the standard library. So we're going to call the insert member of the unordered set. And then we don't know the implementation of it because obviously it's not given here. But you can imagine somewhere inside that insert function, you're going to be accessing various different parts of the state that's associated with this set. And the problem that you're going to run into if both of these things are trying to perform that insert operation at the same time, like in other words, you're inserting into the same set, there's a good chance that, first of all, there could be a data race, because maybe both of those threads could access the same data member within that set, where one of them at least is writing, so you could have a data race. But even if they don't hit the same data member at the same time, like they're not accessing the same state, they're still accessing the same like kind of set of state. And probably the insert function is not written in a way that it could handle the fact that if two different threads are trying to insert things at the same time, that all possible combinations of how the timing could be that things would work. Most likely what's going to happen is the data structure for the unordered set is going to get corrupted in some way. And this is the reason why I say the most likely outcome of running this is probably it's going to crash, because there's probably going to be some pointers in this data structure that like the underlying implementation of unordered set will probably have pointers, and probably due to things being not handled properly, due to two threads doing an insert at the same time, you end up with some pointers pointing into deep space. They're not pointing to the right place, which could be due to various factors. Like the student said, maybe you're reallocating to make more space or something like that. There's various things that could cause pointers not to be pointing into places where they should be. And then when you try to dereference that pointer, maybe you have the good luck that that virtual address is not in your address space and you get a segmentation fault or something like that. If you have bad luck, it could maybe keep running on doing all sorts of weird stuff. But for something like this, my guess is most likely it would probably just crash, because it is a lot of opportunity for it to really go off the deep end, because you're looping a fair number of times in both of these loops. Are there any other possible like problems? I mean, maybe just to be a bit more specific, is there any issue with respect to this calling this contains member function here? Because we have like a whole bunch of adding elements to the container going on here, and then here we're checking something about the container. Is there any problem with respect to this call here to the contains member? See someone nodding their head. If yes, why?
Oh, because it doesn't guarantee thread safety. Even the print operation is not necessarily thread safe either, so you don't guarantee what's going to come out.
Well, maybe I should rephrase the question. So like assuming that things didn't already get totally hosed by the code up above here, which is likely to happen, like you're probably not going to get this far. But imagine that just by some miracle of miracles, like these two threads doing adds at the same time somehow don't manage to completely mangle the data structure and it's still completely valid. This is really unlikely to happen. And then we get down to this line here. Could this, in this case, could this function fail at this point? Because I think you might have been thinking along the lines, things are already hosed, so probably there's no hope. that would be the case. But supposing by some miracle of miracles, we manage to run both of these threads and they don't stomp all over each other, the data structure doesn't get corrupted, and by some miracle, everything works. It's very unlikely to work. But if we get down to this line here, in that case, could this work or not?
I think it'd be fine because of the joins.
Yeah, exactly. Because of these joins here, these joins are going to introduce a happens before relationship. So when we return from the second join, what this would guarantee is that all of the threads have finished executing. And also not just that, but any changes that they made to the data structure S would now be visible to us. So we would at least, assuming that the data structure didn't get completely trashed by these loops, which in practice it would, but assuming it's by some miracle it didn't, and we actually got down to this line, we'd be okay because we'd be guaranteed that all the changes that were made to S would now be visible to us because of the happens before relationship introduced by the join. So when we read this, we'll get a consistent picture of the world. We see this nice data structure, it's not completely corrupted, and we make a conclusion about whether that element's in the set or not. But realistically, like, things would get badly hosed here. So by the time we hit here, even if we got to that line, it's not going to do what you expect. But I was just saying a hypothetical just to see if people were thinking. And it's good that someone observed that because of the joins, if things didn't get hosed by this point, it would actually work at this point. So that essentially there is no real race due to this line here. The problem is with these two add operations sort of racing between one another. Any questions about this example before I move on? Yep.
So about the T1 and T2, like the T2 join after the T1 join. So are they going to execute at the same time, or T2?
Okay, you're asking, this is a good point. I should have maybe done a slight variation on this example. So suppose that I take this suppose I take this line here that's printing out S contains 1000 and squeak it right in between the two joins. So I have like T1 being joined with, then I execute this line, then I have T2 being joined with. Would this be okay? I think this was kind of the point that you were getting at.
Yeah.
Would it be?
Yeah, because I'm thinking like T2 join after T1, so maybe T2 will wait after T1 finish, and then so there will not be data race between these two functions.
I'm not quite understanding the logic, but in any case, unfortunately, the answer you gave is not correct. If I did move this line that prints out, like basically just make line 25, move it up and insert it after T1 join, but before T2 join, then I would have a possibility of a data race, or at least some kind of race condition, because if I move this line here into the middle here, I'm guaranteed that T1 is finished. So I can't have a problem that T1, thread T1 is trying to access this container S. At the same time, I'm checking to see whether it contains some value. However, because I haven't joined with T2 yet, it's quite possible T2 could still be running. And if T2 is still running, then you have the possibility that T2 could be executing an add operation at the same time that I'm trying to execute this contains operation. So you have two people, like two threads that are both accessing the same container at the same time. Unless you're really, really lucky, and in practice you won't be this lucky, bad things are going to happen. In the worst case, maybe get a data race, and then it's undefined behavior. In the best case, they're kind of not touching the same area of memory at the same time, but you're going to probably end up you could maybe possibly corrupt the data structure. I mean, maybe that's less of a problem here, because I would guess that probably this function is not going to mutate the container, but we don't really know the implementation of it, so maybe it's hard to make a categorical statement in that regard. I think I should stop here for today. I just noticed I'm running over time.